Now come back to this another half, and then let us talk about rank. Just now I proved that row rank of a matrix is also column rank, and this common rank I will keep calling a rank. And as you have seen, the proof was computational and it involves the coordinates and so on. But now I want to give second proof, which will be less computation, and with this one should realize that it is better to study linear maps than the matrices. So, second proof. So, this we have given this matrix A, which is Mij. This is Aij, I in I, J in J. But one should think really this is a linear map Fa, which is from the vector space k power j to k power I. Namely, I should tell you where the basis goes. So, the basis Ej, the standard basis Ej here is mapped to the element summation Aij Ei. And note that this Ei on the right side is the basis, standard basis of k power I. So, this is a linear map, and whose matrix with respect to the standard basis will be then the given matrix A. Just also to avoid this confusion between the standard basis here and here, you can also think directly this is F is a map A comes from a map F vector space V to W, and this vector space V is with a basis Vi, Vj, numbered by the same indices as the columns are indices, column index, and this is V, and this is W is a vector space with basis W, and basis of W is numbered by the set I. And if you want a linear map, we just have to give what is f of Vj for all j. But we will define f of Vj by this formula. And this way we do not have a confusion with the standard basis and coordinates and so on. So, therefore, this matrix A, you can think a linear map F. And again, if you take this matrix F, the matrix of F with respect to this basis, this is precisely the given matrix A. So, if I want to prove the rank of row rank of A equal to column rank of A, I will have to prove that, prove the relation. Row rank is nothing but the dimension of the image, that is rank of F. Sorry, column rank is nothing but the dimension of the image space of F, and row rank will be nothing but the dimension of the image of F star. So, note that, let me write it, note that we have proved earlier that rank of F equal to rank of F star. Where F star is a map, if F is a map, linear map from V to W, F star is a map in the other direction. And if you take a basis V here, W here, the corresponding dual basis W star and V star, and we know the relation between the matrices also, that is the matrix of the basis, matrix of the linear map F star with respect to the basis W star and V star. This matrix is the transpose of the matrix of F with respect to the basis V and W. This we have proved last time, and this rank of this matrix, that is column rank of this, is therefore the row rank of this. So, this is rank of M W star V star F star, but this is nothing but the row rank of M V W F, and this is the column rank. So, we altogether we have proved column rank equal to row rank. So, okay, now let us come to the computational part. So, now I want to address, so let me write this as an example. Computation of ranks. Okay, I am not going to discuss numerical examples, 3 by 3, 4 by 4 matrices whose entries are actual numerals. I am not going to discuss them, but I want to do it little bit more theoretical way. So, how does one compute the rank of a matrix more effectively or relatively easily? So, the rank of matrices can be determined relatively easy by using the so called elementary operations on rows and columns, but I will stick to rows first. So, what does one mean by this? So, let us let A be a matrix whose rows are numbered by I, columns are numbered by J, entries in the field K, and I, J are finite sets. And I want to now change this A to some other matrix A prime without changing the row space. So, when I say row space of A, that means a subspace generated by the rows, K subspace generated by rows of A. So, this is same as summation in our notation, summation I in I K R I, where R I is a row of ith row of A. and this is a subspace K subspace of K power j. So I want to get a new matrix A prime from A by doing some operations without changing the row space, so that the row space don't change. But A prime becomes simpler in some sense. So that means I want to get more zeros in the matrix entries of A prime. So if the row space does not change, then the ranks will be equal. And then go and get more simpler. That is the strategy. And what are the row operations we are considering? So we consider the following elementary row operations on it. Okay, there are three types. The first type, that is addition of the scalar times A times a row to another row of A. So that I want to write this in the notation. So A is a scalar, arbitrary scalar, I is a row, so ith row to another row, and j is Rj is another row, so I naught equal to j, and I am replacing Rj by Rj plus Ari. So the new matrix A prime and A, they will only have, all the rows are equal, only jth row will be replaced by this new jth row of A prime. This is one operation. And obviously here you see row space is not changing, because Rj is replaced by this. So I can always recover Rj from this by using Ri. So in this case rank of A prime is not changed. The second type of operation is multiplying a row by a non-zero scalar, by a scalar which is non-zero, A in K, A non-zero. In notation, that means we have a scalar A non-zero is very important, field is also very important, and the ith row is now replaced by A times ith row. So the new matrix will have only the ith row is change, and that will be a multiple of scalar multiple of the ith row. So this is also clear that the row space is not changing. So A and A prime will have the same row space. Third one, interchanging two rows. That means I have two rows Ri and Rj in the original matrix, and now only I'll positions are changing. So Rj will become Rith position and Rj will become Rith position, and this will become jth position. They are only interchanging. So now the row space is also clearly not changing. So this way I am going to get a new matrix whose rank will be same, and I will acquire more zeros. I will give still more concrete example. but also I want to remark here that operations 2 and 3, and I am not going to use column operations, and also I am going to use very sparingly operation 2. Reason being because in the next few lectures I also want to address for the problem for computing the rank of not only a matrices with entries in a field, but matrices with entries in a ring like integers. And for that I will not allow to use, we are not allowed to use by non-zero scalars, because in that case scalars are integers, though integers are non-zero, they are not invertible in the ring. So, okay. So, okay, let us further continue. Okay. Now, I want to recall already when we did Gauss elimination, in the Gauss elimination, we demonstrated that row operations of a matrix we can transfer, we can find a new matrix, so that the rank actually you can see it what it is from the new matrix, and so that will be like this. So let me recall it. So I will write the final matrix here, what we have got from the original matrix. So C11, C22, CRR, and then below that everybody is 0, here also 0, and here there may be some entries, here also there may be some entries. And how did you get this? So we had original matrix here, where CII are non-zero for I is 1 to R. So what did we do first? We first found a top entry which is non-zero. For that, note that we might have had to interchange the columns, because all the columns will not have zero entries, non-zero entries. So we could have interchanged the two columns also. And then once you have a non-zero entry here, we use this to use row operations to make the entries below that 0, and repeat this process. So this way we have got on the diagonal, you see it's not a square matrix. So when I say diagonal, it's a main diagonal. So there will be maybe rows are more, columns are less, and so on. So this is a main diagonal. So some entry is non-zero, and after that it becomes 0, 0, 0. Above that we don't know what it is. So, and because, so here only to note that we have allowed also to interchange columns, but we didn't make the other column operations. And because we are in a field, we could have made actually them 1, 1, 1, 1. If we are working over a field, but if you are not working over a field, still we have managed this for integers also. And here it is clear that the number of non-zero entries on the main diagonal is precisely the rank. So that was what the Gauss elimination also has the similar motivation. Okay, and so another remark I want to make is, in general, computing a rank of a matrices by using the computer software can be difficult and can be more time consuming, just because, and also it may not compute the exact rank, especially for real and complex numbers, because the computer softwares will approximate the real numbers to some decimals, and when the entries become smaller, computer will ignore it, and instead of that it will become 0 entry, and this will mislead the calculation. So, whereas the maximal rank, one can compute the matrices which has maximal rank, that you can do little bit better, that I will come back to when I do it for integers. Okay. So, also next one is, I also want to show that these row operations on the matrices also will allow us to compute inverses of matrices rather easily. Not only compute inverses, also to decide whether a matrix is invertible or not, and in that case what is the inverse. Both these we can do it simultaneously. So, let me write one lemma for that. So, because we are dealing with the inverses of a matrix, I want to start with a square matrix. So, I finite set, and we have a square matrix. A is in MIK. This is a square matrix. Rows and numbers are numbered by the same set I. Then the following are equivalent. 1, A is invertible. That is, there exists a matrix B with AB equal to identity. This is enough, or BA equal to identity. This last time we saw it. One of them will imply the other, because finite dimensional, I is finite, that is very important. 2, the columns of A are linearly independent. And when they are linearly independent, they are correct in number, and hence a basis form a basis of k power I. 3, once you say something about, whenever you have matrix and says something about columns, one need to say something about rows also. So, the rows of A are linearly independent, and hence form a basis of k power I. Fourth, A has a maximal rank. That is, rank of A in this case equal to cardinality of I. Okay, so let us see the proof. Again, proof. I always want to see a proof by using a linear map. So, let us go proof. Let us go to linear map. Remember, our matrix will give you a linear map FA, which is from k power I to k power I. EZ vector here, EZ standard basis vector here will go to summation Aij Ei for every j in j. This Ej in I standard basis, and in this case there is no confusion because the same set. Okay. Now the matrix of F with Fa with respect to the standard basis, this is the given matrix A, and we know, we have proved, a matrix is invertible if and only if the linear map is an automorphism. So A is invertible if and only if Fa is an automorphism. K automorphism. And what is the image of Fa? Image of Fa is the column space of A. By definition, column space of a matrix is the subspace generated by the columns. Cj's are columns, jth column. So the column, what is the statement here? I just want to show you this one, the second one. Columns are linearly independent, that is equivalent to saying it is a basis. If it is a basis, that means f of image of f of A must be the whole. So image of f suffix A is the whole Ki if and only if 2. A first was invertible, but the 2 if and only if this means Fa is surjective. So this means Fa is surjective. But once Fa is surjective, that is if and only if Fa is bijective, that is, it is an automorphism. So that proves one if and only if let's one if and only if 2 it proves, and similarly one if and only if 3. But then instead of that, so then I will apply the same remark to the not to F but the F star, and the rows and columns will get interchanged and so on. So replace Fa by either, if you want in a matrix, it is Fa transpose or Fa star, whichever. Fa star is nothing but this. So then other remaining are equivalent, that is clear. So that proves the lemma. All right. Now about finding the inverse. So now let us take arbitrary n cross n matrix, n cross n matrix A, which is Aij, 1 less equal to I j, and this is a matrix, square matrix of order n. And we are looking for inverse. We want to decide if A is invertible and to compute A inverse if it exists. We consider a matrix X, where X is a matrix but the entries are variables xik. Let me call it small j, small xik. K is j, k is our 1 less equal to I k less equal to n. So, it is also n cross n matrix, but I want to determine xi's, that is why I call them variables, and then I will come back, we will see what we want. So, what we are looking for? We are looking for such a matrix X, so that A times X becomes identity matrix. So, I want to compute this Xik, so that this equation. But what does this equation means? Let us write down. This means what is the ikth entry here? Ikth entry on the left side, ikth entry of LHS equal to, that will be the ith row of A times jth column of X. Not jth, kth column. Ith row of A times kth, ith row of A times kth column of X. So, that is AI1 X 1k plus AI2 times X 2k and so on, plus AI n X n k, correct. This is equal to ikth entry on the right side, but ikth entry is delta ik. This is Kronecker symbol. So, it is a linear equation. In how many variable linear equations? In these variables x1k, x2k, xnk. Now, therefore, I have a linear system of equations, and this linear system, the coefficient matrix so this system of linear equations coefficient matrix is the given matrix A. And we want to solve it simultaneously. Okay. For that, one uses the Gauss elimination. So, use the Gauss elimination. So that the matrix, the matrix A will get changed to the new matrix like this. Diagonal C11, C22, it is a square matrix, C and N. Below that 0, above that somebody. Now, it is clear, if all these C's are non-zero, if all Cii are non-zero for I equal to 1 to n, then there is a solution. The Gauss elimination says, no? And then A is invertible. So, remember what we have done is the following. Let me just go back and show you. See, we wanted to solve this equation, this equation, and we are making row operations in a Gauss elimination on the matrix A. So, the same operations we are making on the identity matrix. So, here when you make the Gauss elimination elementary operations, we have made the matrix A like this. So, the equation became this times x, this times x equal to this matrix has changed. Okay. And now first we decided that it is invertible or not, how to test it, only the diagonal entry should be non-zero. And now in this case what do we do? One, this is all these are non-zero, this is non-zero in particular. Now I start making row operations from below. So then they will get transformed to this, again this identity matrix will get transformed. So that will become, that will solve this x, because this matrix will become identity matrix and then x will become a matrix. So that means I have solved for x also. So this way we can find the inverse. So, if you do it the other way, I just want to remark, if you want to solve instead of this, if you want to solve this kind of this, that also one can do it, but then instead of row operations we have to use column operations. Well, this is also equally simple and it is the same. So, with this I will not like to do a numerical example, but you can just one remark and then we can stop for today. Suppose I take such a matrix, suppose I take a matrix like this A, 3 by 3 case, 1 2 4 0 minus 1 1 and 2 3 8. This is 3 by 3 matrix with rational entries. And suppose I want to decide whether it has inverse and inverse exists not, etc. So what usually we does it, you on this side you write this matrix 1 2 4 0 minus 1 1 2 3 8, and here you write identity matrix and start making operations here, and then you do the corresponding operations here, and then this becomes identity and this becomes the inverse. That is what, but you carry out this, carry the elementary operations to find whether A as A inverse exists and then A inverse. So, we will stop there.